So the first thing I want to talk about is what do we look for when we look at the plates and the straps. And if I look at this cell is in fairly good condition. The separators are here. We have these are rubber separators. The separators should extend above the positive plates, out beyond the positive plates, so that they should separate positive plates and negative plates. Plate colors are pretty good here. You can see the positives look nice and black, the negatives look medium gray. They're kind of consistent in color top to bottom, so that's what we're looking for. Here you can see these little sparkles, and that's exactly what they look like. When you go in there to look at these cells, you're going to bring a portable light source, such as a flashlight. And you're going to take that flashlight, and you'll take it, and you'll hold it about 6 to 8 inches away from the cells, and you'll kind of move up and down and across on the plates and up in the strap area. If sulfate is present, the initial form of lead sulfate looks very glassy as a crystal. And when you shine that flashlight on there, it's going to reflect that light back at you. And what you see here, those little things that look like sparkles, and they look kind of white here, is my flash reflecting back into my camera from those glassy crystals of sulfate. At this stage, those sulfate crystals can be easily converted back to the active material by charging. So if you found this situation, you could put the entire battery on charge, or if it's isolated to 1 or 2 cells, you might put those individual cells on charge. And then if they reappear, then you'd have to go further and figure out what the cause is. And we'll talk more about that later on. So that's what sulfate looks like. If you don't do anything about the sulfate, then the crystals tend to go together and they will actually turn white. And the plate colors will either get a very light brown or cocoa brown, or they'll look charcoal gray. And if that happens like this, where this battery needs to go right now is the recycling center, because you're not going to be able to reconvert that active material back to its original form. And that cell, this particular cell, is ruined. So if you don't react to the undercharge, it's eventually going to destroy the battery. We look at this is plate growth. We can see the covers are actually coming off the cells. And what's happened here, remember yesterday we said the positive plates are shorter than the negatives. So these positive plates have grown. They've touched the support bridge down at the bottom, and now they've got nowhere else to go other than try and push the cover off or crack the jar or crack the cover, but something's going to happen. And the owner here has been trying to put RTV compound in there just to seal it up. But by the time this happens, it's too late. Because on a calcium alloy cell, generally, if we could measure the dimensions of the plate, when the plate has grown somewhere between 4 to 6%, depending on the plate type, that's end of life. That cell is going to have less than 80% capacity. So by the time you've got plate growth like this, that battery is not going to pass a capacity test. Okay? Just to show you what plate growth really looks like, this one I took out, this was on a 5-year-old cell, and the brown is the positive plate. Okay? The gray grid that we see here is the same type of grid that was used to originally manufacture that plate. So you can see that that plate has grown out and has grown down. And that's exactly what they do. So they'll grow out, they'll grow down. And that's what you're looking for. So you can go down, you can take your flashlight down the bottom of the cell and see if there's still a space between the positive plate and the support bridge. If they're down touching the bridge or getting close to touching the bridge, you can see plate growth. If they're growing out past the separator ends, plate growth. Here, we can see some cracking on the covers. This is due to plate growth. This happens to be a C&D cell, and C&D is experiencing cover cracks on their cells for different reasons, but these cover cracks here are plate growth related. It's a valve-regulated cell. The plates have grown out right through the jar wall. And this battery's in service. Okay. And again, you know, some of these things, you go in and you look at that, you point it out to the owner, and they might say, well, you know, we thought something was wrong, but we weren't quite sure. Okay. But that's plate growth. Here, this is a gas turbine. And if we look at this, these are valve-regulated cells. These are actually manufactured by FIAM. And we look at this, and right here, you see that little white right in that area? Because everything looks pretty good here, but there's a little bit of white. And that should catch your eye right away. And if we come in, if you see that, something's going on. And if we look up, the plates have grown and cracked the jar up there. Now, you should be able to find that with your internal resistance measurement as well. But some of these things you'll be able to see with your eyes before you'll be able to see it with an instrument. This one. I always feel that the manufacturers have an uncanny ability to put writing right in an area where they have some problems. And if you look at this, it's a little bit hard to see on this screen right here. But there's actually a crack in the plate, right in this place. And I don't know whether we could, I don't know whether you need to stop filming or anything, but could we turn off all the lights and maybe we could see that, just so I can show them? And you may be able to see it in your book. I don't know how it appeared in your book. You can see it in the book? Okay.
Yeah, right above the A.
Yeah, here it is, right here. You see that crack? Okay, thanks, Tim. And you'll be able to see it when you get the slides. But those things are right there. And sometimes I'll be going through a string, and usually what I do for inspections personally, and you do whatever you'd like to do, whatever you feel comfortable with. But when I inspect things, I inspect kind of one thing. And I just focus. If I'm doing plates, I'll walk down every cell and look at plates. If I'm doing intercell connectors, I walk down and look at intercell connectors. If I'm doing flame arresters, I look at flame arresters. Because if I've got to try and look at it, I just can't keep track of it all, and I probably would skip something. But as I go down a string like this, let's say this was cell 20. If I got to 20 and saw that crack, I'd go back and start over at 1, because I might have missed it. It's sometimes as much as you know they might be there, you might miss them. So if I find it, I kind of go back and start and make sure I haven't missed anything beforehand. Same thing here. These cells, there's a crack here, there's a crack here, so fairly large cracks in the plates. And when you get into some of your high performance cells around the 10, 9, 10, 11-year range, you'll probably start to see some cracks in some of those plates. Okay. When we look at this, what this looks like here is a bunch of iron filings that have been picked up by a magnet. And they kind of just hang down there. And although this looks really ugly, this doesn't present a problem to the batteries. It's a phenomenon known as treeing, like the trees that grow outside, so we call it treeing. There's nobody that's ever given me a good explanation of what it is and why it occurs, except that usually I get an answer that says, well, it depended on the mold temperature and the lead temperature when the grid was cast. And I've come to understand sometimes that that means I don't know. But that's the general answer if they don't know. And because it's a non-problem, you wouldn't take these cells apart, but hopefully someday I may get a cell that has some trees in it that I can have analyzed and see what's really there. But I don't know why it occurs. But the one thing that's important for you to understand is that it's not a problem when you see it. You would just note it in your inspection report. You'd say cell 29 has trees or all cells have trees. Normally it doesn't look this bad because I get to see a lot of batteries, so I see kind of worst cases sometimes. Most times trees will look like this. They'll just look like little fuzz balls down at the bottom. They hang off the negative plates, and they'll just look like little fuzz balls down there. This is a piece of lead, And obviously it was there since manufacture, but eventually that lead will, pushing against the separator, can actually puncture the separator, and you'll set up a plate short. And once you've got a plate short, then you're going to have to replace the cell. Now, visually, it's going to be tough to see plate shorts, and we'll look at plate shorts later. But plate shorts are easy to see with voltage, because what will happen to the voltage of the cell, it'll approach open circuit voltage. Remember yesterday, we talked about open circuit voltage. And I'm going to double check, because yesterday I picked up a non-erasable marker. But we talked about open circuit voltage. For a cell that's 2.15, we add 0.84 to it, and we basically get 2055. And if we had a cell that was 1250, and we add 84 to it, we get 209. So if I'm going down the string, and I'm looking at the cell voltages, and let's pick a number that we're floating at 225, and I see cells at 225, 218, 221, 223, 208, that cell is shorted. There's no doubt about it. Okay. If I see a cell, typically even if it's below 2.1, if it's 2.09, it's a shorted cell. And there are things you can try and do the shorted cell. We'll talk about single cell charging later, which you may be able to do. But once the cell has a short, it doesn't mean that it doesn't have capacity, but it does need to be replaced, because eventually it will fail. Okay? So it's not a situation where you may have to replace it instantaneously. And for that, we look at the gravity. If the gravity is still good and the voltage is low, then we're going to have capacity in that cell. But if the gravity starts to drop and the voltage is low, take the cell out of the string. Okay. These plates, you can see they're kind of starting to buckle and warp a little bit. They're coming close to end of life, and they're going to need to be replaced. This one. If we look at this, does anybody see anything unusual about this picture? Can't inspect the individual plates. And that's correct here. This is actually installed incorrectly. All these jars should be turned 90 degrees from where they are. So they're not installed correctly. Anything else? Excuse me? Gray to gray. Okay. Well, we look at this and we've got gray, gray, black, gray. Okay. But let's look at a couple of things. On lead acid cells, we have a situation where the cells are typically manufactured with positive plates and negative plates, right? And there's always one more negative plate than positive plates. So there's always an odd number of plates in the jar for U.S. manufactured cells and most other manufacturers, but you will find an occasional exception to that. Okay? So you're going to have one more negative plate than positive plate, which means at each end of the cell you're going to have a negative plate. Okay? So what's wrong in this picture? Well, a thing that's wrong in this picture is I expect to see a negative at the end. I expect to see a negative at the end. I expect to see a negative at the end, and I see a positive. Does anybody have any idea what happened? Manufacturer formed it backwards. Okay. When plates are manufactured at the battery manufacturers, they don't know whether they're going to be a negative or positive. And when they're put in the jar, they go through a process known as formation, which actually creates the electrochemical cell. And if the manufacturer hooks up the leads on the formation charge wrong, they will form negative plates as positive plates, and they will form the positive plates as negative plates. So that cell is formed backwards. It should have never been placed in that string. As soon as it was taken out of the box, somebody should have seen that and basically got a replacement for it. The issue many times is that people just don't know what to look for, so it doesn't appear any different to them. All right. The other thing that's wrong in this picture is that remember we said the cells should have been turned the other way. Those are also not the right connectors for those cells. Those connectors are actually for C and D type cell. EnerSys doesn't use that connector. And this was at a gas turbine installation. And what I believe is that the previous battery was a C and D battery. It was a DCU. And when they ordered this, they failed to order the intercell connectors with it, or they didn't get the intercell connectors, but they just reused the cables from the DCU. Now that could affect the performance of this battery because that cable resistance is different than the connector resistance that EnerSys supplies, and the performance of the cells will be affected because if I've got additional voltage drop, then I'll reach end voltage sooner and I'll have a shorter discharge time.